is if I try to change the shape of this cube, I would do that by taking my hands on the two surfaces and trying to shear it to displace one direction while I displace the other in the other direction. For reasons of static equilibrium, if I impose a stress that's going to try and change the shape without putting the body into uncontrolled rotation, that simple shear has to be balanced. That is, if I have a shear stress on this face, I have to have a compensating shear stress on that face, and so on. So simple shear looks like this in terms of the lobe geometry. The other kind of shear which will change the shape is balance shear. Suppose I put compression along one axis and tension, an equal tension, on another axis, so that I'm trying to squash the body sideways and extend it a long time. That's a balance shear. And if these two stresses are equal, that's also a shear stress. So we have tensile stresses, hydrostatic stresses, simple shears, and balance shears. Conveniently, in analyzing stresses, as long as we're in a linear regime, elastic stresses are additive. So for example, if I have stresses in the x, y, and z directions, the strain in the x direction is 1 over the modulus, just add them up, sx minus nu sy plus sz. You can show similarly that the strain in the x direction, and then the stress in the x direction, if I have strains in the x direction, y direction, and z direction, this stress is a rather complicated thing. E over 1 minus 2 nu times 1 plus nu, 1 minus nu ex plus nu ey plus ez. Not a very simple formula, but these things are simply additive, so you can derive this formula without that much trouble. So it's not real hard to see what happens when you have triaxial stresses acting on the system. Well, one of the problems with the Young's modulus and Poisson's ratio as our two measures of elastic properties is that they're not really that closely associated with what's fundamentally happening in the material. If I pull on the material, just ideally, I would not only change its length, but I would change its volume as well. So I'm simultaneously changing shape and volume. If you analyze a material from a fundamental point of view, if you get down and try to calculate or compute or understand at the fundamental level what's going on when it deforms, it turns out to be very convenient to divide the things that happen to the material, in fact, to divide the energy of the material, into two terms. One is a volume term, and the other is a configurational term. When we calculate the energy from first principles, well, some people just brute force it. But if you want to do a relatively simple calculation of the cohesive energy of a solid, you calculate the energy as a function of atomic volume. Turns out that most of the energy that comes from making a solid just comes from changing the atomic volume, irrespective of the configuration. The second thing that you calculate to add to that is the configuration. So I would calculate energy as a function of atomic volume, then I would impose a particular crystal structure and see how that changes the energy. And so I'd have these two terms. Well, in terms of elastic deformation, that is the energy as a function of volume plus a function of shape. So we might try to look for moduli that would be more fundamental. If we look for the modulus that controls the volume, and then the modulus that controls the shape. Those two moduli are called the bulk modulus. Pressure is bulk modulus, fractional change in volume. The shear modulus G, the shear strain is proportional to the shear stress by the shear modulus G. So these are the more fundamental materials. The bulk modulus, which is governing the volume irrespective of shape, the shear modulus, which is governing the shape at constant volume. And if we look at those, we find that it is possible to, there are only two independent moduli for an isotropic material. So I can solve for Young's modulus, I can express Young's modulus and Poisson's ratio in terms of those. And I get these messy looking formulas here. But they actually turn out to be fairly simple. Let's consider the behavior of a solid in terms of the ratio of its resistance to volume change and its resistance to shape change. That is, what's the ratio between the bulk modulus and the shear modulus? And you really just get four cases. First of all, let's consider an incompressible solid, when we call it incompressible. Well, you might think an incompressible solid means that the bulk modulus is very big, but that's not our definition. Our definition is not that it be big, but that the bulk modulus be much, much greater than the shear modulus. That means anytime you do anything to this solid, it's going to want to respond by changing its shape rather than changing its volume. Therefore, it's going to be incompressible. When this is true, it turns out that Young's modulus is about 3 times the shear modulus, and nu is 0.5. Well, if you just go back to here, change in volume, when nu is 0.5, the change in volume is 0. So it's incompressible. What sort of things have this kind of behavior? Classic case is natural rubber. You don't think of natural rubber as being difficult to compress, but in fact it behaves as an incompressible solid. Not because its bulk modulus is so high, but because its bulk modulus is so much higher than its shear modulus that any time you try to press on it, it'll change its shape, basically at constant volume. If we get down to kind of normal metals, we have the bulk modulus about 3 times the shear modulus. That gives us a Young's modulus about 2.7 G and nu about 0.35. Many typical design books will just tell you a metal, if you're making elastic computations with a metal, you assume Poisson's ratio of 3.3, 1/3, and that's not far off. There are a few things that have Poisson's ratios that are a bit different, but that's it. Now suppose we take something that's a very, very strong directional covalent bond. So strong that the B and G are about the same. Bulk modulus, shear modulus are just about the same. Diamond is a case in point. If I do that, Young's modulus drops to about 2.25 G, nu gets down to 0.1, about that. And this would be the case for things like diamond, which have behavior kind of like this. Now let's take an extreme material. Suppose we have a material that is so resistant to a change in shape. Basically, its bonds are rigid. If I try to do anything to it, it will insist that it change its volume but not change its shape. That would be a case in which G was much, much greater than beta. There is no such material. However, in theory, you can have such a thing. And if you did, E would turn out to be about 9 beta, and nu would be about -1. There are no natural solids that have overall Poisson's ratio less than 0. There are solids that have Poisson's ratio less than 0 in certain directions. You pull on them, they actually expand rather than contracting. And there are mechanical engineers in particular have made kind of a game of constructing sort of artificial foams that will have negative values of Poisson's ratio. So this has been kind of a challenge for a certain community that does this. So you'll see a number of papers out there on foams, particularly artificial foams, that have been constructed do in fact have negative values of Poisson's ratio. The thermodynamic maximum would be -1. Minimum, I'm sorry, would be -1. So Poisson's ratio varies between -1 and 0.5. In fact, it varies between about 0.1 and 0.5. So if you're making calculations and you assume Poisson's ratio of 0.3, you're not that far off. Furthermore, if you assume Young's modulus varies with G, you're not that far off either, since the coefficient only goes from 2.25 to 3. So from the point of view of the balance between volume and shear of the behavior of materials becomes a bit more simple. Engineering the elastic modulus. Well, it's kind of hard to do that. And the reason is that elastic properties reflect atomic bonding. Microstructure manipulation just does not have much of an effect on the modulus. You can change the modulus by changing the composition, but with very, very few exceptions, the change in modulus is proportional to the composition, so you have to essentially make a huge, rich alloy before you get any significant change in the modulus. The fact that the microstructure does not affect the modulus is a huge engineering problem. And where it has been perhaps the biggest problem is in the push to make lightweight vehicles and such things. Suppose you want to make a car. You would like to get good gas mileage. You would like to get the weight down. Suppose that for economic reasons you want to make a car out of steel because it will cost less than half of what it would cost to make it out of anything else. You've got a problem because the limitations on the car will be the performance limitations, a good many of them, particularly dent resistance, go with the elastic modulus. That's the buckling behavior. So you can try shaving the body of the car down. I think I mentioned to you earlier, the first car I had a 20 mil sheet bumper. No way you would have dent that unless you ran into something pretty hard. These cars these days, you go out, put your thumb in them, you can dent them up if you want to. And that's because they've shaved that metal off just as much as they possibly can. But you can't shave it too far or it would dent in the wind. Give you a specific example. I used to have a joint project with the Ford Motor Company. We'll go back and just talking to the guys at the Ford lab about what they were doing. And I remember one time they came up with one clever idea. They said, well, where can we shave some weight off? Well, one place we can shave weight off is the roof, because all the roof does is keep the rain out as far as we can see. So let's take the roof and shave it down, shave 50% of the steel off the roof. So they did what they do, which is one reason that automobiles tend to be safer than aircraft, because they can do this kind of thing. What they do when they have new ideas, they just knock off 50 cars, give them to the Ford people on leases and have them drive around Detroit and see how they work. So they knock off 50 cars with these super thin roofs and send them out. Everything was fine until someone tried to take one to a car wash. Car wash has a roller up top. So it comes out, you have two nice big grooves in its roof. So you are carrying another few pounds on your car so that you can go through car washes. And those kinds of things happen. So it would be great if we could do something about the modulus. Unfortunately, we can't. The one example that was successful and is used is aluminum lithium alloys. It turns out that if you add lithium to aluminum, you get a double payoff. The modulus goes up by a surprisingly large amount because of subtle things that happen to the bonding, and the density simultaneously goes down. Now, when you're designing aircraft, the measure of weight you want to use is the specific modulus, E over rho. And E over rho takes a nice big jump if you put in about 2.5 lithium in aluminum. So there are aluminum lithium alloys out there. They are increasingly used in aircraft in applications, and they do a nice job of allowing you to knock down the material and drop the weight of the aircraft. But the real thing that you try to do to control the modulus is composite materials. We have all kinds of materials out there that in fact are very high modulate. Since the modulus goes with the bond stretching, you would say, well, gosh, give me anything that has a really strong bond, and that's going to have a high modulus. And it's pretty much true. So the things that have very high modulate are things like ceramics, oxides, aluminum, glass, quartz, graphite fibers, things that have very, very strong bonding. The problem is, for reasons we'll talk about in just a little while, anytime you get something with a really high bond strength, it's going to be brittle. Brittle as glass, which is an example, in fact. So you have the problem that while it would be nice to use these ceramics and glasses and such things for their high modulus, you really can't use them practically because they break. They break so easily. Wonder Woman may fly around in a glass airplane, but I would not want to. So I'm not protected by this. Who's it, Zeus or Hera? What you can do, however, is you can take these high modulus materials and make them into composites in which you embed them in a matrix that has some ductility and some toughness. And in that way, you can take advantage of the modulus of the material. And this is what composite materials are all about. Fiberglass, which is glass epoxy, graphite epoxy, there's also boron epoxy, silicon carbide aluminum. There are a number of composite materials that combine a high modulus brittle material embedded in a low modulus but ductile matrix to give you a material that has superior elasticity and low weight. And these, of course, are very attractive for use in aircraft and so on. When I first went to work in the aerospace industry in 1968, everyone was assuming that at almost no time at all, at least all military aircraft would be made out of carbon composites. Well, it's almost 50 years later, and it's finally starting to be true. Even the commercial aircraft are finally starting to use significant quantities of structural composites. But you can see the difficulties these people had to deal with, because it took about half a century to make that happen after the invention of the material. And it's because of the difficulty of designing them, putting them together, making them into an airplane, and making it at reasonable cost. Alcoa, who of course wanted to sell aluminum to the Air Force, used to go around with a marketing chart. And the marketing chart had a log plot the cost of a typical military aircraft plotted against the gross national product. And along about in their projection, along about 2010, was already passed. The cost of the aircraft passed the gross national product, so the entire nation could afford one airplane. Well, fortunately, they found a little bit cheaper ways of doing it, so we can afford more than one, but they do get awfully expensive. What about the composite materials? It's important to recognize in composite materials that they come in two basic types, and each has its advantages and disadvantages. In one type, which is a fiber composite, we have elongated fibers embedded in a matrix. So if this is a two-dimensional cross-section, but in 3 dimensions, you would see little individual fibers, and they would all be embedded in a matrix. And it's one-dimensional. If I look to calculate the modulus of these, I can easily show, and it's done here. I won't trace you through the math. Well, really what's happening is, if I pull on this composite, the criterion is the strain in the fiber is the same as the strain in the matrix. And if I just use that, I come to the conclusion that the effective modulus of the composite is the average of the moduli of the two pieces. So if I have something like a graphite or even glass where I have a very, very high modulus in the fiber, I can make a unidirectional fiber composite that has a very high modulus because of this law of averages, and one of these numbers being very large. And for things that can use this high modulus, like shafts or golf clubs and so on, this can be a very, very useful configuration. But it has a problem. I'm only getting this modulus in one direction. If I consider what happens if I start trying to load this in other directions, suddenly my modulus goes away. So to use this kind of configuration in aircraft, for example, I have to find a way to make the loads that the aircraft sees unidirectional. And there are ways to do that for good many parts of the structure, and more that's being done, but it is a challenge. A much more forgiving configuration is what we call a particulate composite. In that case, instead of having these fibers running the length of the material, let's just chop them up and embed them. This is the way normal fiberglass is, for example. You have your matrix, and you have chopped glass fibers just all over the place. So effectively, you just have a whole bunch of glass particles sitting in this matrix. When that is the case, then to a very good first approximation, the criterion is that the stress in the fiber and the stress in the matrix has to be the same. Well, unfortunately, when I compute the modulus from that, I turn out not to average the modulus, but to average the reciprocal modulus. Now, this averaging the modulus, means that my performance is dominated by the high modulus phase. When I start averaging the reciprocal modulus, that means the modulus tends to be dominated by the low modulus phase. So from the perspective of getting isotropic properties and manufacturability and all that kind of stuff, this particulate composite is a much better choice. But from the perspective of getting the modulus up, it's not nearly as good as the unidirectional composite is. The kind of run-of-the-mill composites that we use, like fiberglass, you have an awful lot of things made out of fiberglass, and they are basically particulate composites. The modulus is good, not super, because you have to average the reciprocal modulus, but it's good enough that the stuff is worthwhile. It's very light, the modulus is reasonably high. But you don't use it for really intense structural applications, challenging structural applications. For those, you need fiber composites, and that gets you into all kinds of problems in assembly and design and so on in order to use them. You can go even further. You can also use 2D or 3D configurations. That is, I can take a fiber composite, make a cloth if you want, where the first plane has fibers in the X direction, the second in the Y direction, back to the X, back to the Y, and so on. Those came in at a very early date. We had them in the late 60s. And they are less directionality, but you do lose a considerable amount of the modulus benefit. And of course, you have the manufacturing problem. So these are used, but there are always challenges. Particular composites, lower modulus, more isotropic, they're relatively tough. They're much easier to form, and they're used for multi-axial loads in situations that are not all that challenging. For example, if you look at even a conventional aircraft like a 737 or such, the underbelly of the 737 is fiberglass. It doesn't really carry much of a structural load, and so it's, you can do that to save weight. Although I recall hearing one guy up at Boeing say, gosh, if all airplanes had to do was fly, life would be very simple. They had grounded a 757 down in Dallas a couple of years ago because a baggage truck, not too ferociously, ran into the side of it. Well, if it's metal, you get a small dent. If it's fiberglass, you get a crack that runs the length of the underbelly. You've got to ground the airplane until you can replace the whole part. I had a fiberglass car. In fact, when I came out here, a Lotus Europa, great car, fiberglass, very, very light. But if anybody banged the side of that, you were looking at just a really major repair because of the extended damage to the fiberglass. So these things are very good from a theoretical point of view, and they are becoming used in advanced engineering such as aircraft, but it's been a long, hard slog because of all of the difficulties involved in really making them work. Well, plastic deformation, this is a good place to stop, because our time is up, so we'll pick that up on Wednesday.